Solving general chemistry problems, thermodynamics. Look at a couple of problems. Steam reforming is a reaction that produces hydrogen gas from hydrocarbons such as methane. Here's the reaction below. What is its equilibrium constant at 25 degrees Celsius? Is it a useful reaction at this temperature? What would be its equilibrium constant at 1100 Kelvin? Does this reaction favor products at low or at high temperature? Well, the answers are that K at 298 Kelvin is 1.23 times 10 to the minus 25, an extremely small number. By contrast, at 1100 K, it has the value 26.8. This indicates that the reaction favors products at high temperature. Here's another one. Mercuric oxide was the first source of oxygen gas when discovered by Priestley in 1774. He heated HGO and found a gas was given off. How hot would you need to get a sample of HGO in order for it to start to decompose to liquid mercury and oxygen gas appreciably? Well, the answer is about 566 degrees Celsius. Do you know how to approach these kinds of questions? Let's look at how we can consider changes in temperature when dealing with chemical reactions. We have seen this most famous of equations that relates delta G to delta H and delta S for a reaction. Notice how delta G will change quite explicitly with temperature. Most of our tables of thermodynamic data have been created based on reactions at 298 Kelvin. So by referring to tables, we can find delta H naught and delta S naught at 298 Kelvin and use them, along with 298 Kelvin, to find delta G naught. Most tables give delta G data also. So you could have found the same answer directly from the tables. But what does one do at a different temperature, or say 400 degrees Celsius? Well, you could just use the new temperature. Don't forget to always use Kelvin for temperature in these equations, 400 plus 273, 673 Kelvin. But what about delta H naught and delta S naught? Can we just use the same values? Well, the answer is no and yes. Delta H and delta S do themselves change with temperature. So strictly speaking, we need to find their values at 673 Kelvin, and then we can use the same equation and solve for delta G naught of reaction at that temperature. How do we find these values at this particular temperature? The enthalpy and entropy data are derived from measurements of constant pressure heat capacity as a function of temperature. Over the years, scientists have made careful measurements of heat capacity over wide temperature ranges for many substances. These are tabulated. From this data, enthalpy and entropy data can be exactly calculated over the same temperature range. These data have been fit to many fitting functions. The simplest is to just fit them to a quadratic equation and report the three coefficients, A plus BT plus CT squared. You might find this in some physical chemistry textbooks. By comparison, the complexity of the fit can improve the quality of the results. NASA provides access to a very thorough database online. Their enthalpy data are fit to an equation of the form A over T squared plus B ln T over T plus C plus DT over 2 plus ET squared over 3 plus FT cubed over 4 plus GT to the 4th over 5. Each substance has its own set of parameters for A, B, C, D, E, F, and G. The same set of parameters in a different function are used for entropy calculations. As you can see, a student could calculate this for all partners in a reaction and then use the same products minus reactants to find delta H naught reaction and delta S naught reaction at any temperature, and then find delta G naught reaction and hence K. This is what is done for precision work. If you work in the energy industry, you would need to be this careful. If you're working for NASA developing a new rocket engine propellant, you'd have to be this precise. However, for general chemistry, it has been decided that this is a lot of extra math that risks clouding your chemical learning. So we are always working on the assumption that delta H and delta S do not change with temperature. The numbers we calculate at 298 Kelvin from tables are used at all temperatures. So then all we do is insert the new temperature into the delta H minus T delta S equation, and we have delta G at the new temperature. How much of an error is this? Well, for small temperature changes, it's not too bad. But for large temperature changes, well, consider ethane, C2H6. From tables, we find that the data at 298 K is delta H naught of formation minus 84.68 kilojoules per mole and S naught 229.6 joules per Kelvin mole. At 1000 Kelvin from the NASA database, however, we obtain delta H naught of formation as a minus 105.04 kilojoules per mole and S naught equal to 331.68 joules per Kelvin mole. The differences are significant, but for general chemistry, we still ignore the difference. Just use 298 Kelvin data for delta H and delta S, but delta G will have different values at different temperatures. You just need to know that there is a better way and that you could use it if you had to, but just use the simpler calculations here. There is another approach to this issue of varying temperature. We know the connection between the standard Gibbs energy of reaction and that reaction's equilibrium constant. Delta G naught equals minus RT ln K. Placing this into our equation and rearranging allows us to write ln K equals minus delta H naught reaction over RT plus delta S naught reaction over R. Now this is the same equation, we're just solving directly for ln K rather than delta G naught of reaction. There is one more step we can take, however. We can create the Van 't Hoff equation by writing out this expression for two temperatures, T1 and T2. Subtract the equation involving T1 from that involving T2. Recall that when you subtract logarithmic terms, you can combine them into a single log expression by dividing the two terms. We get ln of K2 over K1 equals minus delta H naught reaction over R times 1 over T2 minus 1 over T1. Here the two values for K are the equilibrium constants at the two temperatures. The advantage? The entropy term has cancelled out. If we have an equilibrium constant at one temperature, we can find it at another temperature by only finding the standard reaction enthalpy. We do not have to find the standard reaction entropy. This is a common general chemistry problem. The challenge you will have is getting the subscripts in the right order. If you remember that it comes from subtracting equation 1 from equation 2, you should be able to reproduce it very easily. So this is the Van 't Hoff equation in its integrated form. We use it to relate equilibrium constants at two different temperatures. Also, here is another warning of a technical mistake students commonly make. 1 over T2 minus 1 over T1 is not at all the same as 1 over T2 minus T1. Watch out for that, and be sure that you are always using absolute temperature, T in Kelvin. And it's worth pointing out another way these equations can be used. Look again at the relationships in this equation. Look closely at the structure and note how it can be put into a form of the classic linear equation that is so well suited for graphing. Ln K is the y of the equation, and 1 over t is the x in the equation. The other terms are seen to be the slope m of this straight line graph and the y-intercept b. If we create a graph of ln K versus 1 over t, this data would come from a series of experiments performed at different temperatures, then the slope is minus delta H naught over R, and the intercept is delta S naught over R. One makes the graph, determines the slope and intercept, which when multiplied by R, the gas constant, provides an experimental approach to determining these two fundamental thermodynamic properties. Watch the sign of the slope and the negative sign in the definition. A positive slope would be made a negative by the definition so that the enthalpy change is negative, which makes it an exothermic reaction. A corresponding situation arises for endothermic reactions. So let's return to those questions at the beginning. Here's the first question about the reforming reaction involving methane. Our strategy is to first find the formation data for the reaction participants, determine the standard reaction enthalpy and entropy, products minus reactants, and determine the standard Gibbs energy of reaction with this equation, and turn that into an equilibrium constant. This table shows the formation data for the four reaction participants. Here are the calculations for the enthalpy and entropy of reaction. We determine the standard Gibbs energy to be 142 kilojoules per mole. Put this into the exponential relationship for K to find K equals 1.23 times 10 to the minus 25. K is very small, which means the equilibrium lies way towards the reactant side. No meaningful amount of reaction occurs. At higher temperatures, we calculate a new delta G naught of reaction. The only difference is using 1100 K rather than 298 K. Because of our assumptions in general chemistry to use the same values of enthalpy and entropy at all temperatures, we can use the same numbers as before. The new standard Gibbs energy is minus 30 kilojoules per mole. Note that the sign has changed, and we can expect a change in the behavior of the reaction. Substituting it in gives us a new value for K of 26.8. We can use the reaction at this temperature to produce H2 gas. The other question was about the thermal decomposition of mercuric oxide. Start with the same strategy as before. Formation data from tables, reaction data. Here's our table of data. And here's the calculations for the standard reaction enthalpy and entropy. But this time we are looking for a temperature, one wherein the reaction is producing oxygen. Now there are many ways someone might interpret the phrase appreciable production of oxygen. I suggest looking for K equal to 1, such that the products are favored as well as the reactants. This requires, now look at the equation defining K from delta G, that delta G naught of reaction equals 0. Put this into the equation and solve for T. Remember that this will be T in Kelvin. Convert to degrees Celsius if needed to give 566 degrees Celsius as the answer. Certainly some oxygen will be released at lower temperatures. Without more specific guidelines in the question, this is a reasonable suggestion. If K is just 0.1, which happens at just below 500 degrees Celsius, the O2 pressure would be 100 millibar, which compares favorably with the 210 millibar found in the atmosphere.